Dear Heavenly Father, we thank you for this day, and we thank you for the blessing which thou hast given to us. We're grateful for this chance we have to learn together. We're grateful for all that we have, and we pray for protection to be with us and our families. And we say this in the name of Jesus Christ. Amen. All right, ChEn, do you want to real quick? Let's look at the schedule. Okay, so we are here today, all right, it's the 12th. All right, so the schedule keeps moving back as we cover what we cover. So we got through energy equation last week. We're starting on shell mass balances today. We will certainly spend this week still doing material on that and the mass equation. We will have an exam next week. My best guess is that it will be Friday next week. If it takes us all week to do this, we may have and if we still have a little mass equation left to do on Monday, we'll do that and then we'll start review. But anyway, we'll adjust there. Okay, we'll see what happens. I put 2 review days in sort of to absorb. So, only get 1 review day. I'll have 1 review day. I think we'll be okay with that. And then on the exam day, I'll just skip it over learning speed, and it'll be probably 2 or 3 hours. Sort of have the full cutoff time, and will be a take-home exam, so we won't have class. It'll just be on learning speed and run over however many days. So say it's on a Friday, I'd start it on Wednesday after class, and you can turn it up until we have class again on Monday or something like that. So that'll kind of be how it goes. So we'll see what happens, but I wanted to sort of note that we have an exam. I think you've had exams in your other classes. That's what I've heard, is that you've had an exam today in which class? Thermo. Okay, is that where everyone is? They're like, oh, thermo is gonna kill me. I gotta go study for that. I can't come to transport. All right, so anyway, let's get that out. I know we have Brian and both Zachs. Hey, Brian, are you in quarantine too?
No, I'm just going to take the thermo test at my apartment as soon as class is over.
All right. So then we're 1, 2, 3, 4, 5, 6, 7, 8. So we're missing Gloria, missing her today, and Dan. Dan. All right. Dan. Is he coming to the other classes? No, he's not, because he's just repeating this one. All right. Well, let's hope we see Dan. All right, so today we're on shell balances. So we kind of did this weird thing in the schedule where we did momentum shell balances and then energy shell balances, and then we did momentum and energy equation, and now we kind of skipped mass. But we did mass at the beginning, so I don't know why that was the way it was in the schedule. I thought maybe there was some broader reason, but it doesn't look like it. So anyway, so we're kind of going to take a step back a little bit to shell balances, and then we'll do a couple of example problems here, and then we will move forward and do the mass transfer total equations. So from what I can see about mass transport relative to energy and momentum, they're all kind of they have these analogies, but they have these things that are unique about them, right, that make them kind of different. So in momentum, for instance, momentum is a vector, so then you get tensors all over the place. That makes that kind of a hard thing, right? Energy is maybe the easiest, but it couples with momentum. So you kind of got to learn a little momentum, and then you go, oh, we got things like viscous dissipation terms and stuff that comes in there. So that's one reason why we do it after, maybe, right? In mass transport, you have mixtures, and that makes it kind of hard, right? So now you can't just do a single equation. You have multiple equations and multiple unknowns, sort of because you have a mixture. And then, of course, you can also couple heat transfer and momentum transfer in with mass transfer of mixtures, and so it can get kind of messy. So at the beginning, there's a couple tricks we kind of have to learn about mass transport. And then when we go into the equations, some of it's just, I think, understanding all the connections between these things. And the problems explode really quickly. Like if you want to do something that has mass transfer, fluid flow, and heat transfer in it, you know, like let's say you're going to do an evaporating film and it's got all of these things, like it can get messy really quickly. So I'm still trying to figure out as I go through this chapter, like what exactly are the important things to sort of highlight at this stage. Because I want to give us a fair like overview of what's in mass transfer, but I don't want us to like spend 3 weeks, right, just talking about all the various cases, you know, that are there. So that's what I've been working through. So we'll start today with just reviewing some shell balance stuff, and I'm hopeful we can get through actually quite a bit of this because I think it's pretty easy. So we'll see how much of the algebra we really do. So let's start off with a review of shell balances and mass plots. It's been a while since we've seen this stuff. So we can do the shell balances, right, just like we did for momentum and total mass. We did one for total mass and for energy. And we had this procedure, you remember. So I said the first thing we do was to ID the geometry and the direction of transport. Okay. And then the second thing we did was we wrote a steady state balance. Right. So that was these, you know, we started doing balances on these 3D systems. These were going back to just the steady state balances. And in this case, it's going to look like a sum of mass flow of some species. So if we're doing some species alpha, so this is species alpha, we have a mass flow of alpha in minus mass flow of alpha out plus any generation terms. So these are usually chemical reactions. We'll talk a little bit about those at the end. Okay, so we write down the steady state balance, all right? And then we substitute flux expression. And you remember, this is where we had our constitutive relationship, where we had the flux force relationship. We plug that in and we take the limit as delta V goes to 0, right? So we've done that a lot now, right? We get derivative terms. And then step 4 was we ID the boundary conditions. Okay, so we look at the problem, we figure out what are the boundary conditions, set those up. So these two guys together, this gives us an ODE BVP, right? Some boundary value problem that we can solve. And then step 5 is just math, right? Where we integrate the differential equation and solve for, you know, use the boundary conditions to solve for the unknown constants and find our solution, right? So that's the step, that's the procedure we go through. And then, so the sort of thing with this that we have to remember then, is the kind of unique thing about mass transport part is we need to remember what are the flux expressions for the species mass. So what are the fluxes? Okay, so we had N alpha is the total flux. We said that was rho alpha V plus J alpha. So remember, we had something for both mass and for moles. So this is the total flux in mass units. Okay, and then this was this, you know, this is of, I guess, species alpha. Okay, and then this term here was the convective flux. And this was the diffusive flux. And remember that we had a fixed law for the diffusive flux. So we had J alpha is equal to minus rho DAB for binary system, gradient of the mass fraction of alpha. Is this looking familiar? Do you remember this? Okay. So I'll write down, we also had one for molar. So we got molar was capital N alpha equal to C alpha V star. And you remember V star was the molar average velocity. Well, that's kind of obnoxious, but this is what it is. Okay. And then our mole flux was minus C DAB gradient of mole fraction. So some things maybe to remember here that are kind of useful, just quantities to put in your notes. Remember that, for instance, the total density is equal to the sum of all of the species densities. And equivalently, the total concentration is equal to the sum of all the species concentrations. So that's useful to remember. I think it's useful to remember that the mass fraction is rho alpha over rho, and the mole fraction is C alpha over C. Okay, and then I think the most important thing left to remember is rho V is equal to the sum over N alpha. So this says the total fluxes of everything has to lead to my total mass flow of the solution, right? So this is, you know, mass times velocity divided by volume. And then this is also, you know, the sum of the fluxes, right? Which says that's the mass per area per time, you know, in suitable units, right? So those have to be equal. And the same thing for the mole version. Okay. All right. So those are just some like equations to get down to remember. So I think we should hopefully all be familiar from earlier. But it's been like what, like 4 weeks or something since we talked about this. So I thought. Okay. So I'm going to take kind of a different tack. So for the last couple of weeks, we've been doing like lots of equation, and then sort of derive the example at the end. In this one, I'm going to do some examples. We're going to sort of highlight the principles from the example. Okay. I think these problems are simple enough. We can sort of afford to do that. So let's start with this one. Of a gas. All right, so let's set up a geometry. We're going to step through these 5 steps here for the diffusion of a gas and a solid. We're going to use this, I put up here boundary conditions. We're going to use this to review the different kinds of boundary conditions that might be possible, and to just think about those in the context of mass transfer. So that's really kind of the point I want to highlight here, but we'll sort of step through everything along. So we've got some parallel slabs. So we have some solid, and the solid has a height h. And we have, suppose we have some gases flowing above and below this solid. So this might be, for example, like a thin polymer membrane, okay, that we're using to separate two gases. So down here, we're going to have concentration we call WA naught, and up here we'll have WA1. Okay, so you might imagine maybe A is like CO2. You're using this membrane to try and separate CO2 from some stream, right? Have a high concentration here, low concentration here. You're trying to get CO2 and oxygen both diffuse across the barrier. You're hoping that one diffuses at a higher rate, right? So you can get separation. And we will assume that WA1 is greater than WA0. So I guess it's diffusing this way. So diffusion's a method. Anything we can say, so let's say that I've got this thickness H, but I could also have an area of that membrane, which I'll call LW, length and width. So just assume I have some rectangular flat membrane. Okay, but this is going. All right. So this is, this is one, right? This is step one in our shell balance problem. We drew the geometry. Okay, we find the direction of transport. The direction of transport's in the y direction, in the negative one direction. Okay, so we draw our shell here. Okay, the shell is of thickness delta y, and we go to the 2, where we do a steady state balance. Okay, so I think by now you guys should be familiar enough with this that you should be able to do a steady state balance. So I'm going to give you 3 minutes to do the steady state balance real quick. Okay, and then I'm going to write up my answer, and we'll see if yours compares with mine. All right, we got it. Got it at least all the ways. So who can tell me what you get for the flow in term? What do you think, Tyler?
I don't know, I wrote the mass flux times area.
So what's the mass flux? What expression did you use?
I started with just the N alpha.
So N, yeah, I'm going to call it A, because alpha is like a generic one, and A I called A over there. Okay, NA, and
And then times LW.
LW. Okay, so it needs to be NA in the Y direction, right? So we could just say NA, but let's be a little precise. And then remember that we need to have it at a certain side, right? So like I would call this one, for instance, like y down here, and then y plus delta y. So this will be at y plus delta y, right? Because it's above, right? All right, Mark, what'd you get for out term? Yeah, that Mark. Sorry, you're both like, now it's confusing. Yeah. Mark McDonald.
Pretty similar. It's n alpha y at y until w.
LW. Okay. Christina, what'd you get for a generation term?
We don't have any because you don't have a reaction.
Perfect. Okay, was 0. Great. Okay. So now what do we do next, Andrew?
I believe we divide by something. Usually it's like the volume LW delta Y,
Yep.
and then take the limit as delta Y goes to 0.
Okay, so we're going to take the limit of delta y goes to 0. Now we're going to have NA y equals delta y minus NA y at y divided by delta y, right? Which is what we got in divided that by the volume. Now we take that limit, that's just a derivative, d dy of NA y. Okay, so that's step 2 and a little bit of step 3, right? So in step 2, I said write this balance out. Step 3 is take that limit. And then we need to plug in the flux expression. That's the other half of step 3. So what we had here, I think I just erased it. We said that NA was equal to rho AV plus J, right? So there were 2 parts to it, the convective flux and the diffusive flux. So for a solid, I can write this as the y component first, NAY is rho A dy plus JAY. Okay, now in a solid, what's the velocity? Well, it's 0, right? It's a solid, don't have, net motion of fluid, so that part's going to be 0. So that one's 0. So then I just get 0 is equal to d dy of JAY. And we said that J was the Fick's law, right? So that was equal to rho minus rho DAB AB of gradient of WA, which I guess in this case we don't need gradient, we just need d dy of WA. So now we can plug that in, 0 of d dy minus rho DAB dWA y. Okay. And if we assume that the diffusivity is a constant and that the total density is a constant, which are pretty good assumptions in this case, I'm just going to get d2WA dy squared equals 0.
Dr. Tree, can I ask you a quick question?
Yep.
What did you do to take out the rho AV term and the NA, the mass flux on the bottom right there?
What did I do to, what did I do?
We lost the rho AV term on the step before that, and I didn't quite catch that.
Oh, why is this 0?
Yes.
Yeah, just because it's a solid. So there's no velocity, right, in the solid.
Oh, okay. Thank you.
Okay, so this is, that's our differential equation, but now we need boundary conditions. So that's step 4 is the boundary conditions. So let's talk about boundary conditions for a second. So this process, right, like this step up through here looks just like the same thing we've done again and again and again, right? So let's just talk about the boundary conditions and think about what the different ones could be. So the first boundary condition we could have would be constant concentration. Okay, so that would be the case if over here I have two, gases flowing really rapidly, such that anytime there's a little change out here, it whisks it away really fast, and I have, constant concentration right over that. All right. So in this case, right, we'd have WA equals a constant, or we could have XA equals a constant if we were doing it on all basis. Constant concentration, Dirichlet conditions, okay? That one's pretty straightforward. Another thing we can have is a constant flux. Okay, so this would be NA equals a constant, or big NA constant. All right. This is sometimes often 0. Right. So the 0 case is, if I have like a wall or something, right, where I have no flux allowed through that case. So maybe this is, instead of something flowing up here, this is just a wall, right? And then I can saturate that membrane with something, but nothing, right? That's going to be a different boundary condition. The next one is symmetry or anti-symmetry. Okay, we've seen this one before. This is where we say the derivative is equal to 0 or WA is equal to 0. That's the symmetry and the anti-symmetry. And this is when we know the solution is either even or odd, right? So if I know that, I have some domain and I can flip over, it has to be the same on both sides. I know my solution has to be even, so therefore I can say that the derivative must be 0 at that point of symmetry. Or if I know that if I flip it over, it's reflected, then it's odd, and I say that WA is 0 at that boundary. That eliminates that part of that boundary. We've seen this guy before, boundedness. Okay, so like we have some cylindrical or spherical coordinate, we might say that the concentration must be less than infinity, right? Or the derivative has to be bounded. Okay, just some physical case if we have some singular solution in the middle of the domain. Okay, so up till now, these all look like the same in momentum and energy. Okay, one we saw in energy that we didn't see in momentum was a convection condition. Okay, in the convection condition, we have NA y is equal to K times WA naught minus, say, WA infinity. So that would be the case where instead of WA naught, I have a WA infinity out here. Okay, and the flow is slow enough, okay, that right here is WA 0, right at that boundary, but there's some difference between WA 0 and WA infinity, right? So in the constant boundary condition, or in the constant boundary condition case, this flows really fast so that WA naught equals WA infinity, right? You can kind of see that here, this flux goes to like infinity, right? When K goes to infinity, and then those guys have to be equal. Or in other words, I can divide by that, and then that goes to 0 over here, and those have to be equal. Maybe that's a better way to see it. What's up, Andrew?
Is a mass diffusion code?
Yes. Yep. Mass transfer coefficient. Right. So this is not either one of these cases. It's not a constant flux case because it's got this variable in here. It involves both the value at the boundary and the derivative at the boundary. So this is called a Robin condition. Okay. So apparently, he got to get a name for the boundary condition, even though he just combined Well, traditionally knowing conditions together. All right, and then the last one, which it doesn't happen really in either of the others, is chemical reactions. Okay, and chemical reactions can come in through the generation condition, which I guess I erased. Just didn't answer that for us. So right, so we have no homogeneous reactions. If we have a heterogeneous reaction, then this can specify the flux of the surface. So look at something like NaY is equal to some function of the concentrations. I'm going to erase that right there. Usually it's a big N. NaY is some function of C alpha. So let's see there. Okay, at the boundary. Okay, so there's an example in the book where this is, I think they call it like K double prime CA, or something like this. Right, we have a first order reaction at the boundary. Okay, so at the end we'll talk a little bit more about that. Before we'll talk a little bit more about chemical reactions. Okay, so if we're going to solve this problem here, we have to know what the boundary conditions are, all right, in order to be able to solve it. Let's pick this one to give us something more interesting than just the straight linear profile that we would get if we picked, say, constant concentration. So let's pick that guy. So we will assume then that the flux, is equal to this, and so and then we'll do this at just one boundary. We'll assume constant. So let's assume, I think I did in my notes. Let's assume at the top that I have a constant boundary, and at the bottom I have this mass transfer relationship. So we will write that as WA at H is equal to WA1, and WA at 0 is equal, or not WA0, NA at 0. And little n, AY at 0 is equal to that. K WA naught minus WA. Okay, so let's do those boundary conditions. Does that make sense? I'm just picking a problem to work for now. But. Okay, so from there, now we're on to step 5, which is math, right? So we have to integrate the differential equation. There'll be 2 unknown constants, and we have to use the boundary conditions to find them. So who can tell me the solution to the differential equation? What do you think? Mark? Just want to have asked you that.
All right. You just take the e squared WA over dy squared.
Yep.
Put the dy over, and it makes a constant.
Yep.
And then you integrate it again.
Yep.
That's yc plus another constant.
Yep. So exactly. So we're going to get, C1 times y plus another constant C2, right? It's linear. That makes sense, right? If I have the second derivative with 0. Okay, so now I can solve, now I can take these 2 boundary conditions, solve for them. So one of them is, if I take the first one, WA at H, that's C1H plus C2. And that has to equal WA1. Okay, easy enough. I can also notice if I put in 0, because I want to find out what WA0 is for this guy. I'm going to need to know it. So let me do that too. WA at 0. Well, 0 goes in for the y there, right? So that's just equal to C2. So that makes my life a little easier. I know that C2 is WA0. I don't know what that is, right? That's some unknown still, what that value is, but it's useful to not have this extra C2 floating around. So I can rewrite WA1 then as C1H plus WA0. Okay, so now I need to use my last boundary condition. Okay, and in that one, I need to know what NAY at 0 is. Okay, well, NAY at 0, we said that was equal to this guy, right? We said it was equal to minus rho DAB dWA dy. Well, Mark integrated too fast. We did it all in one step. But we can write that back down. We can write that dWA dy is equal to C1. Right? I mean, he said it, I didn't write it down, so maybe he didn't do it too fast. So I don't want to blame him too much. Okay, so now we can go over to NAY and say NAY at 0 is still going to be C1, right? And that should equal minus rho DAB. I guess we just said it's C1. What am I doing? Oh, I need the mass transfer. I need this. That's what I need. So I know it's C1 because of this equation, right? I know it's dWA, and I can say that's equal to 0, so that's fine. Do I? Can I? Do I need to put? Let's just be a little more. We'll call this minus rho DAB dWA y. Let me make that minus rho DAB C1. I'm happy with that. Okay. Now I'm going to say that that's equal to K WA naught minus WA infinity. Okay. Now I can find C1, right? So C1 is equal to minus K over rho DAB WA naught minus WA. Okay, so I think we just need to take that and plug that back in now, right? So I have WA is equal to C1, which is minus K over rho DAB of WA naught minus WA infinity times Y plus C2, which is WA naught. Okay, so this is fine, except we don't actually know what WA naught is, right? So like as an answer, it's kind of useless. So let's see, how did I set up with that? What we want is to find it in terms of WA1, not WA naught, right? So I have this relationship here between WA naught, WA1, and C1. I just found C1 right here. What I'd like to do is eliminate WA naught, right? Because that's not very useful to have it in terms of this thing I don't know. So this is like when you do these problems with the Robin boundary conditions, you end up with this thing where this looks just like the solution we had before where it's linear. But when you don't know WA naught, that doesn't tell you anything in a way, right? If you wanted to plot the solution. So let's find WA naught, and then we'll just say this is our answer, but we'll find WA naught, and we can plug it in. So to do that, we have WA1 is equal to C1, which is minus K over rho DAB, multiplied by WA naught minus WA infinity plus WA naught. So what I need to do is invert that to solve for WA naught in terms of WA1 and WA infinity, right? Did I miss an H? Should there be an H right here? Okay, so this is just kind of a pain because I just have to multiply that, right? WA1 is equal to minus KH over rho DAB WA naught. And I'm going to have plus another WA naught minus plus KH over rho DAB WA. Right? And then this I can do 1 minus KH over rho DAB and pull out the WA naught and solve. So I get WA naught is equal to WA1 minus KH over rho DAB WA infinity divided by 1 minus KH over rho DA. I feel like, did I make a minus sign error anywhere? Okay, so these are, I'm just going to leave that there. Okay. So, the kind of nice thing about this is that we can see what goes on here in the two cases. So look at this expression from me. This tells us what the solution is. I'm gonna draw this. So if I think about 0 to H, the y direction like that, and then this is WA over here. Suppose this is WA not WA1. Okay, what this is telling me is that I have some solution that looks like that, right? So if I make this, let me make this WA infinity instead of WA naught. I don't know what WA naught is. That's my interest. Okay, so now what happens as K changes here? So if I make K really big, okay, that would mean I should get back the case where WA naught is WA infinity. So if I make K really big, this term dominates that term, right? And that term dominates that term, and so those things cancel, and I get WA naught as WA infinity. Okay, that's good. So when K goes to infinity, I get this solution, right? And then if I make K go to 0, then that's the case where I have nothing, I just have stagnant at the bottom, and my flux should be 0, right? Because that's what this one says here, the flux is 0. So when K is 0, that guy's gone, and WA naught equals WA1. And then I get a flat case here where K equals 0. Okay? So that's kind of satisfying to go back and recover your intuition and think, like, what does that profile look like? Well, it's going to be a line where what's happening is I'm setting the slope by changing K, right? So as I change the mass transfer coefficient, I'm changing the slope of that curve and what that profile looks like, right? And I can, if I make it really fast, I can drive it all the way down to equal. If I make it, turn it off, I can make it fill up and just fill up the membrane with A, right? Okay, so that's that is it. Questions about that?
Dr. P, I just have a question. Yeah, why do we think about solving for WA naught in this case, but like in most of our solutions in the energy equation, we would just leave it in terms of T naught. Would we not?
If we have a T naught, is the T naught, like usually what we get to pick is like the T infinity, right? And so if I have like a metal and I'm gonna heat it up, then, you know, I'm using that as my boundary condition. Like a lot of times in chemical engineering, we're talking about like we have some solid, and some liquid in between, but we're talking about heating. So it's really easy to control the temperature of that solid, right? Like you have this aluminum or wood plate or whatever, and you heat it up and it's gonna have a constant temperature, right? And so it's a big bath relative to this. But in a diffusion case, right, or in a case where you have mass transfer, it's often hard to ensure that you have that constant concentration. Like physically, the way you do it is like in the gas case, right? It's like by blowing, you know, this gas across it. So it's just, I think if I were to go back and look at it, what happened is we just assumed more often that we had a constant temperature because the physical cases are such that that's more common. Doesn't mean it has to be, right? But it just, that happens to be the case more often. Does that make sense?
Yeah.
So, and then in mass transfer, so it's kind of like, you know, experimentally, what can you control? What can you not control? That ends up dictating the kinds of problems that you sort of look at as examples. All right, so we got 2 minutes left. So let's just set up the next one. Start on the next one. So maybe something to think about. Okay, so diffusion through a stagnant film. Markers, write it down. It's kind of fun though. It's fun to swim. It's hard in these rooms. I realize like the ceiling's so low. I have no arc. Can get, you know, I'd rather just give that a little pause. Okay, so there's this complication that we kind of skipped over when we did this solid example. Okay, I think Zach kind of brought it up when he said, what happened to the velocity? So there is a complication. Okay, we said the following things. We said in a binary mixture, we had Na is equal to rho AV plus JA. We said NB was equal to rho BV plus JB. We also said that rho V is equal to NA plus NB. Okay, so if I have a case where I only have diffusion going on, so suppose I, you know, take the same case that I had before where I had two areas, okay, and I have diffusion of one of them, all right? If I have a diffusion of A, you know, I can't know what the total flux of A is without knowing the velocity, right? And diffusion of A, and there's diffusion of B, so there's like cross diffusion. But the total velocity is the sum of these guys. So of these three things, right, like I have to be able to figure out and solve them simultaneously. They all depend on each other. So, or in other words, diffusion can cause a flow, right? Because it's moving mass. So, you know, it can cause a bulk flow. And so when I, you know, and this is basically, this is a complication. It's a result from the fact that I have both a mixture. Okay, that's one of the things. And then the second thing is that diffusion causes bulk mass flow. Or it can cause, maybe it's a better way of saying it. Okay, you can imagine a special case where the diffusion of A is exactly the same as the diffusion of B going backwards, and then you have no mass flow, okay, but you can have a mass flow. So we have to do something about this, okay, in order to solve these problems when we have velocities, all right? And so there's sort of two cases, okay? Two ways to do this. So I'll call the one the intuitive way. And the other, I'll say the math way. Okay. So in the intuitive way, what you do is you pick some value for n or v that seems obvious from the problem. Okay, so this one is a pick either NA, NB, or V. Okay, turns out because we know these three relate, if I pick one of those things and I say I know this, then you can solve the problem. Okay, in the math way, you just solve simultaneous equations. Okay, for NA and B. Okay, I know enough. If I just plug in and I want to solve two differential equations, I can do it. Okay, in the intuitive way, you just pick one and then solve one differential equation. So this is two equations. This is one equation. Okay, the reason I bring this up is because your book does the intuitive way. Okay, and I think it's confusing. So they'll just say like, oh, and in this problem we know NA is equal to NB, or NB is equal to 0, or the velocity 0 or something, right? We just did an intuitive way with the solid. You can see there's already a little bit of question about, oh, what do we think about that? All right. So if you don't like the intuitive way, if you read the book and it confuses you, we have the math way, okay? And we'll talk about why this next time, okay? So I'll go through this a little bit, the math way, and show what are the principles that we're allowed to use in the intuitive way. And hopefully that'll make that a little clearer. Okay, so I just wanted to give us a preview for next time so we had some heads up about that. You can think about that, come with questions. Okay, so I got for you a good one.